Let me
Yeah,
start. Okay, yes, go ahead. Thank you.
Okay, so I'd like to thank the organizers for giving me the opportunity to speak here. Of course, it would be really nice if we could all be now in Dublin. I'm hoping it's sunny where you guys are, but it's sunny here, so it would have been nice to be there. But I think it's really great that this workshop is taking place anyway, because there's been a lot of very interesting talks, so thank you. So perhaps it's not really surprising what I'm going to be talking about in this community. My usual talks all start, but with the words that string theory on ADS 3 cross S3 cross T4 is integrable. So probably the first slide you can all give by now instead of me. But if you dig a little bit deeper, this is just some slogan, right? So let's dig a little bit deeper, what we know, what we don't know. And the first thing that I want to kind of stress is that it's good to when we think about this background, it's not really one string theory or one family. So we're used to ADS 5 cross S5, where you just have one background and really one integer set of charges, integers worth set of charges that supports this background, namely how many D3 branes there were originally. In this case, actually, in ADS3, you really have to specify how many Ramon-Ramon charges there are and how many NS-NS charges there are. So it's not good enough just saying, here's my background, it's integrable. I have to consider, there are in fact many such backgrounds specified by Ramon-Ramon and NS-NS charges. And strictly speaking, you have to specify D1, D5, NS5, fundamental string charges. You could even cook up T-dual versions where you have D3 branes instead of D1, D5s. So you have to specify which charges you have. So the second thing that's a little bit different to a more conventional setting is that once you've specified what are the charges in this background, then there is quite a lot of different moduli. In particular, typically these backgrounds have got 20 moduli. But I want to simplify today's talk. So that's quite different, right? We're used to ADS5 typically, and there's really just one lambda that you can tune how you want to. That's your one modulus. Here, there are 20 of these moduli. But I'm going to simplify the talk today. And I want to really talk about the pure NS-NS background with 0 Ramon-Ramon charge. And that's kind of an interesting background, as I'm sure you all remember, but maybe if there are some students in the audience, I'm going to go a little bit slow. Hopefully, I'm sure this is familiar to everyone else. There's a really nice description of this pure NS-NS background because it's due to Maldacena and Oguri, which is a WZW or two-dimensional conformal field theory on the worldsheet description. And that description is valid only at a very, very special point in the moduli space. So again, there are strictly speaking 20 moduli, and the story is quite complicated in that sense, but there's one modulus which is quite analogous, it turns out, to the Toft coupling, and that's the Ramon-Ramon axiom. So as we all know, yes.
Excuse me. Actually, do I understand correctly that you claim that the theory is integrable for any moduli?
Yes.
I see. Okay, that's a strong statement. Thank you. So,
but let me clarify, Sergey, as I'm sure you know, what I'm saying is that the zero winding, zero momentum subsectors of the closed string are integrable no matter what the charges and no matter what the values of the moduli. And I'm claiming that on the basis of having an S matrix which satisfies Young-Baxter. Now,
so moduli, no of this moduli do not change the S matrix. Actually, even if you turn on the NS-NS B field.
The NS-NS B field is completely irrelevant because I am considering zero winding sector. Plays no role.
No role.
So maybe we can carry on the discussion at the end, but just to say briefly, there are 20 moduli, and 4 of them affect the closed string spectrum in the zero winding, zero momentum sector. And they affect it by changing this ubiquitous function h. So 4 of the moduli, including, so that's why I don't want to get into all this counting of moduli. There's all these moduli enter through this function h in some as yet undetermined way, and you might as well just forget about them and just think about the Ramon-Ramon axion. The Ramon-Ramon axion plays exactly the same role as lambda does in ADS5 cross S5, or h, or more accurately, yeah, in a, lambda enters the function h of lambda in ADS5. That's of course fixed, but in ABJM, for example, it isn't. So here you have a function h of C0.
Okay, thank you.
Okay, but sorry, I didn't mean to sound discouraging about the questions. Actually, I really want to hear questions from people. So please, if there are more questions, just obviously interrupt and let me know. So if you take the ADS3 cross S3 cross T4 background just with NSNS charges, you might be interested in that theory because at one very special point in moduli space, you know exactly what its spectrum is. And because of the work of Maldacena and Oguri, using techniques which are a slight, well, okay, that's really unfair, which are a generalization of what we all learn in our first year string theory course, right? You end up with some creation operators, which are essentially free. There's some on-shell condition that comes from the Virasoro condition, which you can solve easily because it's just a quadratic equation. And at that point, the spectrum is very well understood. Now, away from, yes, I think I've said that, right? So this is the special point where C0 modulus is equal to 0. And you really know everything about this theory at the special point, not just the spectrum. People have calculated, 3-point functions, partition functions, checked that the partition functions are modular invariant. That was hugely important result, which we don't stand any chance of doing in ADS5 for foreseeable future. But there's always a plus side and a minus side. And the minus side is that you can turn on you would like to turn on C0, right? You'd like to move around in this moduli space rather than just be at some special point. And unfortunately, this is entirely hopeless. So turning on C0 in this WZW language and trying to do some kind of conformal perturbation theory. Well, conformal perturbation theory is hard enough, but here you would try to be adding to the action a Ramon-Ramon field in the RNS formulation, and this is notoriously difficult, right? So when ADS CFT first came along many years ago, people were trying really hard to quantize string theory in the RNS formalism with Ramon-Ramon fields, and it's too hard, essentially because the vertex operator for the Ramon-Ramon field is a spin field, and these spin fields are exponentials of local fields, so it's quite horrible to add. And then you might hope to do this at first order. So of course you could do it perturbatively, and there's this heroic calculation of Cho, Collier, and Yin who did this, I think, at first or second order. And you can calc for some very special states and you can get some results. But in general, CFT techniques, they're just not going to. They're not powerful enough to tell you about the spectrum. Now, of course, we all kind of like integrability here, and the fact that in the Green-Schwarz formalism rather than the RNS formalism, we know how to deal with Ramon-Ramon fields, right, for a very long time. And here, what's nice is that, well, maybe in not your first string theory course, but maybe in your second string theory course, you'll remember that the Ramon-Ramon free-form field strength, which is related to the two-form potential, is not actually equal to just DC2, right? That is not gauge invariant, it turns out, as you would naively assume, but it has this extra correction. So even if the Ramon-Ramon charge is 0, So you set C2 equal to 0, and there won't be any charge when you integrate it. As soon as you turn on a non-zero C0, because your background has got some NSNS freeform flux, the Ramon-Ramon field strength also turns itself on. So that's kind of a nice thing that happens. Namely, you turn on C0, and you automatically, in the Green-Schwarz action, have couplings for the fermions and so on, which include not just the couplings to H, but also to F3. And this model is, of course, something, so this Green-Schwarz action is something that people studied, and initially Ben Hoare and Arkady Zeitlin and Stepańczuk, and together with Tom Lloyd, Alessandro Sfondrini, Olaf Olsen-Sachs, and myself, we followed on from that. The Green-Schwarz action was studied in the presence of an F3 field and an H field. What I'm trying to say here is that the Green-Schwarz action in the pure NSNS charge theory, so just the WZW theory, but with an axion turned on, it's the same action. And so integrability, using, as we showed in this paper, gives you, and the dispersion relation for massive particles was done by Ben and collaborators, was calculated. So we know the exact dispersion relation, we know the exact S matrix, and we know the exact crossing relations. Okay, so what I want to review is, a little bit of each one of these three things, what we know to date, and maybe a little bit of progress in those directions. But yeah, so please, maybe this is a good point for me to stop and see what if people have any questions of what I've said so far, or where I'm heading. No, okay. In that case, let's start with the mixed flux kinematics. And so the dispersion relation here is, well, you see, there's this parameter, I switch colors in writing. There's this parameter K, which is the Vezzumino-Witten level. So that's an integer, right? That's this famous thing that if you have a WZW model, this guy has to be an integer for the theory to be well defined. And this H, this is the one that I guess Sergey was asking about. H is a function of the axion. And what I was trying to avoid saying, just for shortness of time, but it's also a function of 3 other moduli. So there are 4 moduli out of the 20 that enter this function H. Of course, we don't know what the functional relationship is. That's something that needs to be worked out. If I set K equal to 0,
Can
yes.
I ask a question? Actually, why don't you know how the fields enter in H, at least perturbatively?
Yeah, perturbatively, I think probably to some leading order is just linear, right?
I have no idea. It's
yeah.
just you can use the sigma model and compute it, right?
Absolutely, yes. To some, so sorry. So when I said we have no idea, I mean the exact expression. We have no idea.
Okay, thank you.
Thanks. So there are 2 types actually of excitations, depending on whether you have a plus or a minus. And you see that only happens in mixed flux. So, and when mass is equal to 1, of course, as already alluded throughout this workshop a few times, but let me say it again, there are mass equal to 0 excitations and mass equal to 1 excitations. The mass equal to 1 excitations are the ones that Dima apparently loves very much. And the mass equal to 0 are the ones that I suppose Alessandro and I like quite a bit. But anyway, so for mass equal to 1, you see this plus. For mass equal to 0, this plus or minus doesn't make a difference. It doesn't change anything. But if mass is equal to 1, these are different functional relations, and we call them left and right movers. And this left and right, I just want to pause here so to make sure we know when you see a capital left and right, in case it appears anywhere, I'm referring to target space symmetry. So ADS3 cross S3 has got some supergroup symmetry. It's a product group because the dual CFT, the dual CFT2 is 2-dimensional, so it has a holomorphic part and an anti-holomorphic part, or left and right moving, and that's what this left and right refers to. It does not refer to worldsheet left and right. So just two species of excitations. Who cares? It's just a name, but not on the world sheet. Okay, so as you all know, it's not nice to work in energy and momentum. It's much nicer to work in Zhukovsky variables. And we relate them, the momentum and the energy in the usual way for the Zhukovsky variables, but the shortening condition is a little bit different. Okay, so if I set in these equations k equal to 0 and m equal to 1, then you would all recognize this as the usual shortening condition, but with plus or minus. These are the left and the right shortening conditions. Now, the thing that is new here is that the dispersion relation, right, here's the dispersion relation, is not periodic. Right, if k is equal to 0, this is periodic. And so there's this really weird feature actually of the Ramon-Ramon background, that you have this 1 + 1 dimensional integrable quantum field theory, right? Not spin chain, but I'm on the string theory side. This is quantum field theory. And somehow I'm only allowed to consider momenta between 0 and 2 pi, and I should not consider other momenta. That's very strange from a QFT point of view, right? And here, yes.
Can I ask a question? So it's not periodic, but so here you said that m is equal to 1 or 0, but in principle you could have other values of m as well, right?
Yeah.
Like bound states.
Yeah.
So it's true that this thing is not periodic, but this non-periodicity is a little bit like reshuffling around between different bound states number. I don't know if that makes sense. Maybe you're getting there, but
yeah, you're way ahead of me. Way ahead.
All right, sorry.
I'm far slower. So, but all I want to do is to say that, well, you shouldn't really restrict it. So in the Ramon-Ramon case, right, you might, as a naive quantum field theory guy scattering stuff on the world sheet, you might think, okay, well, I should consider all momentum, right? But that would be silly. It turns out that you shouldn't do that because you'd have a really huge degeneracy of states. Right? But here, there's no reason. You should genuinely consider all, for physical excitations, all real momentum. So what I want to do is just plot. So you can solve, for example, the left Zhukovsky variables. You can solve these shortening conditions in terms of momentum P here. Is that clear to people what that formula reads? Can you see it? I tried to use a crayon, which was obviously a mistake. Let me see. I wonder if we can make this a bit better. No, not with my limited technological skills. So if you're not seeing that fully, it's just the usual Zhukovsky expressing the Zhukovsky variables in terms of momentum and mass, right? And the only new thing that you wouldn't have, unless you worked on mixed flux, you wouldn't have seen is some k dependence. And what I want to do is I want to plot what these Zhukovsky variables look like when you vary the momentum. So I'm going to show a few of these slides, but let's first start with one that's a little bit simple. So let me start with just this blue curve. So above the real axis, so what I'm doing is I'm plotting the Zhukovsky variables for p between 0 and 2 pi for now, and real. And you end up with this contour here for x plus if you are a mass 1 excitation. If, like Alessandro has just asked, you would like to instead be a mass 2 excitation, so a bound state, you would be a slightly higher bump, right? And if you're an x minus, you're just below the real axis. And the thing that I want you to, the only thing I really want to point out is that these, let's see, that this point over here does not match up with this point over here. That's precisely because the dispersion relation is not periodic. In the pure Ramon-Ramon case, what happens is you get to here, which is, I'm going to get this wrong, but let's say it's p equal to 0. And you would come out at exactly the same height if you were just slightly bigger than 0 and slightly smaller than 0. You would come out at exactly the same height. You would just loop around. But now you don't.
Sorry, Bogdan, I do not see your mouse.
Oh, sorry.
So
What
I
I'm
do not
saying
know
is,
what you plan. Yeah.
yeah, I will be switching to a different app for the next talk. That's for sure. Here, I'm saying if you is close to zero momentum, p equal to 0, and then if you, but slightly positive. If you, and in the Ramon case, if you went to slightly negative momentum, you would come out somewhere here at exactly the same height, and you would just loop around from -infinity to +infinity. That's why the thing would be periodic. But you come out at a slightly different height that's related to k, if you want. So the other thing that's going to feature quite heavily is, I'll show a slightly better diagram just now, but the other thing that's going to come out a little later on in the talk is that if I plot the same diagram, but with mass equal to 0, I get this funny bulb-like object, which we decided to call, well, we didn't want to call it a spring onion, we called it a scallion, which is, I think, the American word for spring onion. I don't know. So that's the mass equal to 0. And the reason I'm plotting that guy is because actually all the region outside of it is where the physical Joukowski strip, the equivalent physical Joukowski strip will be. So in the pure Ramon case, that was just a circle. And everything outside the unit circle was where the physical Joukowski excitations were, and you could move analytically continue. You didn't have to stick, right? You didn't have to stick to these curves that I've drawn. You could analytically continue in momentum as long as you were outside of this yellow curve. Okay, any questions at this point?
Can you comment a bit on how this thing changes as you change h? Like it moves a little bit around this curve, right?
It doesn't really move them, but it's probably does something I can't remember off the top of my head. The important thing for me that I wanted to explain was the k. So the k is the thing that raises the -infinity side of things compared to the +infinity.
Like in ADS5, by changing h, you would span essentially all the upper alt plane for x plus except the unit circle.
Yes, so I think it does that. It raises everything relative. That was what it has to do. Okay, more questions? So here's a much nicer picture of the same sort, and the scallion is now in black. So of course we shouldn't restrict to just these ranges of momenta. We should consider all ranges of momenta. And now that I've drawn here in, or rather Olaf has drawn here in red, the mass equal to 1 Joukowski variable. And this is the guy we've been talking about. Oops, oh dear. This is the guy we've been talking about just above. But if you go to different ranges of momenta, then on this side, for positive momenta, the scallion extends. But on this side, you get a kidney. And I didn't draw here, but if you drew the next, we'll see the next diagram, you would get kind of bubbles appear. So now you see you've got the scallion, and you've got a kidney, and you've got bubbles. Those are the mass equal to 0 Joukowski curves. And just directly above, if you try to squint and see the first of those contours is the mass equal to 1 guy. And it goes directly above the scallion and it goes into the kidney. And it comes out of one of the bubbles and it goes around the bubble and comes back in. So these bubbles and the kidney are joined secretly. But it's just not clear from this diagram. And what I'm really telling you is that the physical region is not really just one Joukowski plane or one thing outside the unit circle in the Joukowski plane, but it's just the whole kind of multi-cover or compactification of all these Joukowski planes. And the physical region is outside the thick black line that the scallion, kidney, and bubbles.
When you say physical region, you mean the place where like physical rapidities of things that are like components of bounces and so on live? Is that what you mean?
Yeah, exactly. So I mean just the equivalent thing as the physical strip, the equivalent thing as being outside the unit circle in the usual Joukowski style. So you can freely analytically continue and move around a little bit here and there. Now, this was a left scallion, Kidneyan bubbles. If you flip it around, you'll get the right one. I'm not showing it here. And so that's kind of the bottom line for what happens. What the kind of emerging picture of the kinematics of these excitations. Anyway,
Bogdan, I'm not sure I got you how you glue them. So each square is complex plane of X.
yes.
And a kind of you glue X negative to X positive, and it's I even don't know what I mean. I do not know how to. Like you go to infinity, really.
Yes, exactly. So it's a bit like doing tan. It's just much more complicated.
Doing what?
Tangent, tan, the trigonometric function tan. So,
yeah.
but you sort of come out, and you come out on the next one as you increase theta, tan theta, right?
Right. Okay.
So this is just a much more nasty combination. But
I also have a similar probably question. So how do you define physical region? Again, just the region where x plus minus are greater than 1 by absolute value?
Oh, no, right, that's no. I define it in essentially the physical region is just everything outside of this scallion, because you can't, it's because
why? That's the question. Why is it?
Yeah, so that's what these contours are for, right? So if I have momentum P real, and I take, these contours are trying to show, maybe we look at here. These guys have got mass equal to 1, 2, 3, 4, and 5, right? And you can then form bound states, physical bound states, which each one of them sits, each one of them will be in this physical region. It'll be a combination of excitations sitting on, let's say, mass equal to 2. The constituents of the bound states will sit at mass equal to 2, mass equal to 1, mass equal to 3, mass equal to 1, mass equal to 1, and mass equal to 3, and so on. So then you can see how, if you analytically continued, you're going to fill out the full plane. Right? If you change the momentum from being real to being real plus a bit imaginary, you're going to start thickening out those lines. Is that all right?
Not quite. I still don't follow you. Why should you care about real values of the momenta?
Well, I don't
momenta,
know.
if you can see the physical region, momenta can be any complex number.
Yeah, so I think I'm saying the same thing, right? Start off with real momenta, because you know that's a proper excitation.
Yeah.
And I've shown you the contour.
Yeah.
Now make the momentum complex.
But you don't make it complex. All these lines correspond to real values of the momenta.
Yes, so okay, I'm not drawing it. They'll thicken out, right? If you start adding an imaginary part, they will start thickening out, right? Because the bound state guys.
I don't want to care about bound states, just a single particle, say massless particle, right? You have a massless particle.
No, I'm talking about massive now.
Oh, massive. But I thought this black guy.
That's right. So that's like the circle, right? The massless circle is important also in that case. In the pure Ramon case. I mean, all I'm telling you is how does the circle, right? You know that the Zhukovsky variables give you outside the unit circle in the Ramon case, give you where the physical excitations are. Now I'm saying this unit circle deforms when K is non-zero, and this is what it looks like.
So I have maybe a question a bit related to what Sergey was asking. So suppose that I say instead that I want the physical region to be, I look at this first kidney, as you call it, right? And there is a curve that bends back. There is some curve here. I'm not sure if I can point it, right? That bends back, and then the other ones continue on. And I say that the physical region is everything inside that curve, between that curve and the thick curve of the massless guys. What will be wrong with this definition? It's also a definition, right? And it's also
I mean,
some
you can also go out
there. I mean, what goes wrong when I go out? I mean,
I'm not sure I follow.
What is the
you can go.
characteristic that tells me that it's fine to go out of that thing and not, or not? Do you have physical semi-classical bound states that for a fact exist? I guess that's what I'm asking.
Yes, I mean, so if you ask for physical bound states, then they will sit on the components of the bound states. I guess that's why I was drawing the contour. The components of the bound state will sit, for example, on the third contour or first contour, the -1 and the -3. So and that will give you a bound state with a physical momentum, a real physical momentum, the combined one, which is real, and the bound state will be a 4, m = 4 bounds.
But the fact that these boundaries exist, you're saying that they exist because they can exist, like they're allowed kinematically, or you actually check? Because I wouldn't be surprised, for instance, if somebody says, well, if the level is k, you can have up to k bound states, say, right? And the others you cannot. You should.
In a 45,
like
yes. So in a 45-minute talk, I've been suppressing the k. K for us will be large, and I don't really want to get into that discussion. I mean, it's. I think my
k have something to do with the number of curves that bend back at each kidney.
No, not in an obvious way. Maybe, I'm not sure.
Okay, thanks. Sorry.
Oh, maybe it does. Sorry, let me.
Because
I will have to.
With how much up the lines go, right? Every 2 pi, so it should be really.
Yes, no, I think you're right. Yeah, that's right. Yeah, I think basically you join every k line down.
Yeah, that's why I was saying that maybe k bound state is not so.
Yeah, so I think
and that would restrict your space, for instance.
That's right. So it could be that somewhere further up there is a restriction. I guess I don't really care about that for now. And also, it's not clear to me that there will be such a restriction. So I don't.
No, I'm not saying that there is. I'm just saying it's a logical possibility.
But I think for the purpose of the next 10 minutes.
Yeah, I shut up. Sorry.
Perhaps we can. Yeah. Okay. So the thing that I want to finish on for this part of the talk is to say that turning on this axion, the dispersion relation, well, as Alessandro and others also know, becomes essentially relativistic. Well, you see all this term drops out and you end up with something that doesn't quite look relativistic, but then you can shift the momentum and you end up essentially with E = plus or minus P. Well, Kp. And in this limit, you end up having world sheet left-right movers. So that's why I did all this song and dance before about capital L and capital R, nothing to do with world sheet. But here, as you turn off the axion, you end up with modes on the world sheet, the fundamental excitations, the dispersion relation, which just is relativistic, so on the world sheet. So you have a world sheet left mover and you have a world sheet right mover, and actually you sort of have this funny doubling of degrees of freedom, right? Because you have to, as you take this limit, you have to decide, do I keep just the right mover or just the left mover? Do I keep my momentum bigger than 0 or smaller than 0? You have to keep, rather, sorry, I should have said both. You end up with the chiral degrees of freedom on the world sheet. And that's, of course, a hallmark of a world sheet CFT. Okay, so I better carry on with the S matrix part if I want to get anywhere in this talk. By the way, what time did I start?
You saw 7 past or 8 past, so let's say 10 past.
Okay, thank you. But yeah, no, let's carry on. So the mixed flux S matrix, I'm calling it the mixed flux S matrix, but for the purpose of today, right, it's the S matrix of the pure NS theory with this modulus. This S matrix is, turns out, you can just go to our paper with Tom Lloyd and collaborators and set H equal to 0, take that limit, and the S matrix is well defined and it's finite. So that's just a check that you can do. And something that's quite nice that happens is that as you send C0 to 0, like I said, you end up with world sheet left movers and right movers. So in this S matrix, you have, when you're sending C0 to 0, when you're sending H to 0, you have to do it carefully. You have to say the momentum of the excitation is bigger than 0 or smaller than 0 for a left or right mover. And what happens is that the S matrix trivializes when you consider world sheet left-right scatter. So you take any of these S matrices that you have, and you send C0 to 0, and the world sheet left and right movers that now appear in this limit, they don't scatter with one another. On the other hand, the S matrix that scatters the world sheet left movers with each other or the world sheet right movers with each other is finite. It's non-diagonal. It's not proportional to identity. And just to give you an example, so you see what it looks like, just so you really see that what I'm getting at, that it really is non-diagonal and that it really is finite and we really know what it is. For the experts in the audience, I'm restricting to SU11 squared rather than SU114, just because the formulas are shorter. But if you take a boson of momentum P and a fermion of momentum Q, there are two contributions to the S matrix, and I'm writing down here just one of them. And here it is, right? You have momentum P and momentum Q, and you have this shift that came about. So this is just one element, and you can calculate all of them if you want to. And of course, I'm writing down here proportional to, because these S matrices are defined only up to dressing factors, which multiply the S matrices. And the dressing factors have to satisfy some crossing equations. And again, you can look at the crossing equations and take the C0 goes to 0 limit to the pure WZW point. And these crossing equations, the right-hand side remains non-trivial. So in summary, the Vezzomino-Witten limit of the integrable S matrix for this WZW theory is non-trivial, it's non-diagonal, and it's not of CDD form, right? It's not of CDD form because the crossing equation for the dressing factors remains non-trivial. Now, this should be contrasted with some conjectured S matrix for the WZW model, which is, as far as I understand, all CDD, but it's only at the WZW point. And if you make this assumption, this conjecture, you can reproduce I think, large parts of the Maldacena-Oguri spectrum. So it's super strange, right, that this S matrix can reproduce this spectrum, but it doesn't attach onto in any way the S matrix that we know from integrability when the axion is non-zero. So I think for me, this has been, like, over the past few years, one of the most interesting questions. I have no idea what the answer to it is. So it would be really interesting to see how to reconcile these 2 points of view, right? Again, C0 plays the role of lambda, the Toft coupling constant. And what I'm telling you is that there's a smooth family all across lambda, and you get it, and it's smooth at lambda equal to 0, let's say, or here the axion equal to 0. And it's still a complicated S matrix at this point. It satisfies Young-Baxter and so on. But it doesn't match with this all CDD prediction. So how can this be, right? I mean, this all CDD form, maybe it has some, I really don't know. This is more by way of me maybe starting a discussion later on, just to throw out some crazy things. Is to say maybe there's some really subtle nonlinear field redefinition, which is only valid at the WZW point. I don't know what those words really mean. Or maybe what another way of looking at it is what happens to the CDDS matrix when you start turning on this C0? Turn it on just a little bit. Does it somehow crash, or does it transform magically? I don't know. So I'd like to, it'd be great if someone gave me an answer for that, or if we could discuss. So, okay, the final topic I want to talk about is crossing. So we've done kinematics. I've shown you what the physical strip looks like. I've talked a little bit about the S matrix for this WZW model, mostly reviewing what we know about it. And now let's talk a little bit about crossing equations for these backgrounds. And so in ADS-free, I'm not going to have time to review. See, I already knew that there's no way I was going to get to this. So I apologize that I would never have time to talk about it. But there are no massless or mixed mass bound states in ADS-free. So what that means is that you cannot stick together a bunch of massless fundamental excitations and make some higher bound state. That's something that just works out because of the massless kinematics. And what's also true is that you cannot take a massless guy and a massive guy and make a bound state. And this is less immediate. This is less immediate to see. But if you, well, ask me afterwards. But basically, it's because the highest weight states of the m equals 0 and m equals 1 modules have got different statistics. One is fermionic, one is bosonic, and that messes things up. So all of this is actually quite nice. It means that the massless and mixed mass dressing phases are very simple. You don't have to worry about any fancy bound state stuff happening. You can just solve them by a Hernandez-Lopez order dressing factor. And I just want to remind you what that looks like in the Ramon case. If you haven't seen this before, then don't worry about the details. But if you have seen it, you probably recognize it immediately. The only thing that's going to be important for us is that you can write the Hernandez-Lopez order. You can write the Hernandez-Lopez order of crossing of the dressing factor, which solves for you odd crossing, in terms of an integral over two semicircles. So I hope you can see in blue, I have a semicircle on the first integral, which is the upper Zhukovsky semicircle. And on the second integral, I have a semicircle. That's not a very good semicircle, is it? A semicircle corresponding to the lower Zhukovsky, x minus for the massless guy. Now, that's a perfectly good solution if your excitations are massive. And it's kind of obviously nicely analytic all the way outside the unit circle, right? Because of course the contours are just around the unit circle. So if you're outside, if your x's and y's are outside the unit circle, you move around, nothing really happens. But
excuse me, Bogdan, what happens if x is equal to 1 in this KLL?
Oh, I have to just shift it slightly, right? That's zero momentum.
Well,
so
you can't shift it, can you? Because you have semicircles ending at -1, 1, don't you?
They'll cancel, yeah, but
they cannot cancel because it's not sum. They would cancel in the sum, not in the difference.
No, but by the time you get into, remember this is just chi, and you really have a theta.
Yeah.
And so they will cancel by the time
no,
they appear.
Why would they cancel? You have x plus, x minus. If x plus is 1, x minus is not 1.
Yes, it is.
No. If x plus is 1, x minus is not equal to 1.
Okay, I don't know what you're talking about, Sergey. I'm sorry. Maybe
well, you have x plus 1 over x plus minus x minus minus 1 over x minus equal.
I mean, x plus equal to 1 is momentum equal to 0, right?
No.
Sorry, is this massless kinematics? Maybe that's
I'm talking. Well, I thought it was a massive case, right?
Oh, I see. I'm sorry. I understand what you're saying. Yeah, you're right. I understand what you're saying. But then, so what is your question again?
So what happens if x is equal to 1? I'm a bit confused.
Well, I can approach it from the outside, right? So in the physical region, I can approach that point from the outside.
Yeah. So what do you get? Do you get something finite?
Well, yeah. So you take the limit as one approaches from the outside, and it's a well-defined limit.
Why is it well-defined? I can't see it. I think actually it will blow up as log.
I think you'll be.
You see, if I close to x equal to 1, so let's x equal to 1. If I if my integral is close to this point, I can forget about log y minus z divided by y minus 1 over z. And then this dz over x, well, 1 minus z would give you log of 1 minus z, right?
Okay, this is the same expression just written out in terms of a single integral. So this is the same expression that you know very well from
yeah, that's why I'm asking this question. I know that at x plus minus equal to plus minus 1, Hernandez-Lopez isn't a nice expression.
But I mean, you can approach, right? But you can approach that point. So I mean, I think I think we're talking about cross purposes. I mean, you can define a curve in the physical region that will approach that point, and it'll give you a nice finite answer as you approach it. And it could be that you need to modify slightly this definition for that one point.
So basically you are saying that x equal to plus minus 1, these are essential singularities of the phase.
I don't think I'm saying that. Can we postpone this to afterwards?
Yeah, okay. Thanks.
I mean, this is not my expression. This is just the usual. This expression here is just the same, roughly the same. The integrand changes slightly, but as you said, that doesn't matter. It's exactly the same expression as an ADS5. So if you prefer to get it from a double integral where everything is fully kosher, then that's fine as well. There's nothing. I don't really think there's a problem. So the thing that I wanted to say, so I was hoping that this was just something that you're all familiar with, is that if instead x and y are massless excitations, then you shouldn't really integrate along these semicircles, because the physical excitations themselves with real momenta actually sit on these semicircles, right? So for sure, the physical region of the massless excitation includes the real momentum semicircles. But then, a few years ago, we figured it out in the Ramon case. What you need to do is you just need to deform these contours. If the excitation sitting inside the sky is massless, then you need to deform this contour into a straight line. But you need to do it a little bit carefully by regularizing, because this log has got some branch cuts. But there's a procedure for this, and you can quite explicitly do it. This is a very simple function, and when you're deforming, you stay slightly above or slightly below the real line, and then send epsilon to 0. So we described that procedure. So in the case of mixed flux, for massless or mixed mass dressing phases, this story goes through in a very similar way. You have the same integrand, and if your external excitation x is massive, then you're integrating over the scallion and the kidney and the bubbles. And if your excitation is massless, you should deform those guys to just sit on intervals of the real line, just squish up the contours. And you can show that that satisfies the expected crossing equations. And that yes. Now, similarly, actually the mixed flux odd part of crossing, the one that's solved at Hernandez-Lopez order, can be solved in the same way. So the difficulty always is solving, that's right. I seem to have written the same thing in both cases. The massive odd part of crossing equations are also solved in exactly the same way. So you have this essentially Hernandez-Lopez-like integral, but now integrated over these scallions, kidneys, and bubbles. What's more complicated to figure out is what happens for massive even parts of crossing. This is where the meat of the BES phase is. And what we've done in recent work with Olaf, and hopefully going to appear soon, is we've adopted this approach that Gleb and Sergey used in ADS5, of considering a BMN expansion to start off with. So there, I'm hoping that Sergey will not ask me too many questions about this formula because it's his formula. So this is just the expansion of the Zhukovskys in this kind of BMN-like limit with this parameter zeta. And this was already, and you can adapt this to the mixed flux background. So you can't use this particular expansion, but you can adapt it to the mixed flux background. And this was already used in 2014 by Andre, Amit, and Olaf when they found the AFS order and Hernandez-Lopez order mixed flux dressing phases. But in mixed flux and at higher orders, this is quite a complicated, this becomes quite a bit more complicated, and there's a bit of freedom that you have in how this equation can be, how this expansion can be expressed. And there's a nice generalization of this BMN expansion that works at higher orders, it turns out, with a little bit of effort. So once you have such an expansion, what you do is you solve crossing order by order, just like Gleb and Sergey did in AFS and Hernandez-Lopez order, and I'm not sure if they went Fever, maybe they went Fever as well. But what you can do is you can write down at each order of the even dressing phase an explicit integral formula for these chi's. So for example, and then you can evaluate this integral. These integrals are integrals over these scallions and kidneys, and you evaluate them by contour deformation, right, and picking up residues of poles. And so, for example, here is an expression, a very simple expression for the next to Hernandez-Lopez order for this chi. And you'll notice that it depends on a parameter S, and this S is related to K over H in this way. It just happens to be nicer to write. So it's basically the ratio. S contains the same information as K over H. And perversely, it's you should set S equal to 1. Well, not perversely, but you see here when K is equal to 0, you should set S equal to 1 for the pure Ramon-Ramon case. And then you would recover precisely the usual correction beyond Hernandez-Lopez order. I didn't write down the next chi4. I could still fit it on one page, but the ones after that are much nastier. And so we've checked explicitly that these expressions solve the massive mixed flux crossing equations up to 15th subleading order, of course, with the help of Mathematica. We didn't write this out by hand. So I think essentially what we have is we have an integral formula for these guys at all loops. It's just that it becomes very hard then to evaluate these integrals at higher and higher order, but we've checked up to 15th order. And what's nice also is that you can sum up all of these guys and you get a sort of DHM-like expression. But it's a little bit more subtle than the DHM-like expression. It's not, there are some, well, let me just say that when you're solving crossing in the Ramon-Ramon case, you use a shortening condition to simplify the right-hand side of crossing. And that shortening condition is not true. There's a sort of shortening condition which sets a certain ratio of Zhukovskys to 1. And that ratio is not equal to 1 in mixed flux. And so that's why you can't just go ahead and solve the crossing equation in the usual way, just by copying all the DHM formulas. That in itself doesn't work. And here, when you're deforming the contours, it's a little bit more subtle. So this is, I hope soon we'll be able to finish that part of the project, and that would give you the complete kind of expression for the exact massive dressing phases. Okay, so in summary, we have ADS cross S free, ADS free S3T4 string theory with an SNS charge. And you can understand it with WZW methods in a very simple way. Essentially, the spectrum is determined by a quadratic equation. But that's only possible to do when C0 is equal to 0. Now, for all other values of C0, there's not a chance in solving. And so using CFD methods. So I think what's really nice is that now instead, if you use integrable Green-Schwarz methods, you're still going to have to work out all the wrapping corrections, and you're still going to have to work out the quantum spectral curve and so on. But hopefully we can learn a little bit more about this pure WZW theory away from the CFD. So I've summarized a bit here that the Zhukovsky kinematics when you have non-zero axion is different. It's really quite different from the Ramon-Ramon or higher dimensional ADS. And what seems to be interesting is that if you turn off C0, you should get an integrable description, a properly integrable description of the WZW model. Okay, so I think this is where I'm going to stop. Thank you. And as the last speaker, I'd like to thank Marius, Juan Miguel, Ana, and Alessandro for organizing this really nice workshop. And thank all the speakers, and congratulations to Dr. Paul Ryan. Thanks.
Okay, thank you, Bogdan.
Thank
For a
you.
nice talk. Okay, you've already had a lot of questions, but I see Alessandro raised his hand. So Alessandro, you have a question?
Yeah, I'll try not to, because I just wanted to ask a quick question and then maybe a little bit of a comment on something that Bogdan has rather asked. So maybe I'll try to give one answer there. So the quick question is this phase that
Alessandro, sorry, you're breaking up.
You are in the process of sort of checking.
I'm sorry, he seems to.
Can you hear me?
Yeah, I can now. I can hear you.
Hello?
Yes, I can hear you now.
Okay, so I wanted to say this phase, this mixed mass phase, does it manifestly reduce to the Ramon-Ramon phase? I didn't quite get that. Sorry.
The mixed mass.
The mixed flux proposal.
Mixed flux. Yes, I mean.
Is it manifest that it goes back to the known phase in the Ramon-Ramon, but by construction, or could there be some subtlety there?
Well, here's a simple answer. So I think, you know, as the limit itself is kind of subtle. So, but just because you're taking a spectrum that's a particularly interesting question, but it's because you're taking a limit where you will recover periodic momentum. But a simple answer could be that if I'm in the physical region, then I can express my dressing phase in terms of CRS coefficients. And those will certainly go over to the CRS coefficients of the pure Ramon-Ramon.
Mm-hmm.
So in that sense, if I ask, you know, if you give me two physical momenta and ask me what is the value of the dressing factor for those two physical momenta, then it'll go over smoothly. Now, I think there is a nice question, but of what happens when you go from real valued momentum to periodic momentum. But I don't know that it's within string theory necessarily super well defined, or it'll be subtle, right? Because turning off K is not something you can really do.
Yes, absolutely.
But maybe, you know, maybe you can still go ahead and set K to be non-integer. I mean, very often people do, right? And take it as a real number for practical purposes.
Mm-hmm.
But yeah, I would expect the value of the dressing factor to go over smoothly.
So, and maybe if the organizers indulge me, because this answer to this comment of Bogdan about this CDD.
Yeah. Go ahead.
And what it happens if you turn. This is basically this CDD S matrix is nothing else than the left-right S matrix. You can compute it perturbatively, and dependent Adhd did it, and you get, you know, corrections in the deformation parameter. So it's just that the whole thing breaks up into 4 blocks essentially, left, 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 right, right, left, right, right. What you call the CDDS matrix is the left, right, and right, left block, which you can get perturbatively. Whereas the left, left, and right, right blocks, you have no hope of getting perturbatively from the worldsheet because you're trying to scatter two particles that move at the speed of light in the same direction, essentially. Which
So I guess, yeah, exactly.
Yeah. But
so the question is, why is it that you don't need? Yeah. Why is it that you don't need the left part?
So I guess that maybe here, that's my confusion. Does this S matrix of the left, left, and right, right, for which you get a TBA, reproduce part of the spectrum or all of the spectrum of the Zumino-Witte model? I mean, do you get the discrete spectrum? Do you get the continuous spectrum? I mean, you have a TBA, but I didn't quite ever get if that actually can be matched with the known spectrum of the Zumino-Witte model, which is written in, like full glory, and is actually quite simple.
Yeah. No, I mean, that's a very high. I mean, spectrum. The TBA, I hope I am not offending anyone, but it's extremely difficult to extract information about excited states from the TBA. And so you would have to take to really compare to the WZW model, you would have to solve the TBA for super excited states.
Numerically, it can be done. And
no, I think it's utterly hopeless. I think it's utterly hopeless.
This thing, right?
The TBA is completely useless at solving. No, but I think the TBA equations for excited states are, I mean, I am not an expert, so maybe someone can prove me wrong, right? But I thought the generic.
For Konishi, right?
Yeah, but that's the specific state. Now you would have to.
Perhaps I can mention, I think because it's a conformal TBA, it's very difficult to find any meaningful expansion parameters. So either you do it exactly, and I think we're not numerically versatile enough to actually do the whole thing, but there's no real expansion easily identifiable for the ground state. For excited state, I suppose it's even worse.
The ground state should be 0, I guess.
The Witten index, yeah. So if you were to compute the central charge, even there we cannot.
But is it continuous or discrete, the spectrum? Maybe that's a different question.
No, so Diego, I think managed to find a few states, right, which had very nice properties. Yeah, in pure Ramon. And mixed, I think it's. I don't think that until now that's been. I don't think the TBA has been formulated very. I mean, formally you can write down some stuff, right? But you needed the dressing phases and so on, right?
Okay, I shut up now.
Okay, thank you. Any other quick questions? Yes, Sergey, go ahead.
So can you please show these nice pictures with physical regions again?
Yes. Those are, by the way, due to Olaf, who is
right.
amazing at drawing the you saw my picture.
I hope he didn't do it by hand.
Yeah, he got a like this Escher etchings in copper, right?
Yeah. So is it kind of X plus minus plane?
But many of them. It's like compact. So you don't have a single X plus minus plane. So between p equal to 0, see, unfortunately, I cannot draw on this because of this stupid program that I'm using badly. On this interval is what you, the other way. This interval is what you think of as the Zhukovsky plane. It's p equal to 0 to 2 pi, and it's a whole infinite plane, goes off to infinite.
Why would it go to infinite?
Well, that's just what happens with Zhukovsky variables.
So so on your horizontal line you have p. What do you have on your vertical?
No. Sorry, no. Sorry, maybe I explained this badly. It's this formula that I tried to draw in crayon. Do you recognize? Can you see this formula, Sergey?
Yes, x plus minus L.
Yeah, it's the usual formula, except it has this k dependence, right?
Yes,
you know this formula.
But it's kind of.
And now all I do is I plot this with real momentum, and I show you these contours, and each contour corresponds to a different mass.
Wait. You plot what? X plus minus?
Yes, yes.
So
this is
on the horizontal
is
line,
Zhukovsky.
wait. So
It's a
on the-
complex
Function
number.
parametric plot. Function parametric plot in Mathematica.
So
Yes.
you have on the horizontal line you have imaginary part of x plus on real part
normally
of x plus,
you can
real part of x plus, and on vertical imaginary. That's what you plot.
Yes, yes, yes. So in the usual case, in the Ramon case, you would have a bump like this.
Yeah. Okay.
Doesn't this picture go off to infinity? Sorry.
Yes. It goes off to infinity. But what I'm
Yeah.
saying is, in the Ramon case, you see, you just go back. If you go beyond p equal to 0 or 2 pi, you come back, and you keep going around and around the same bump, roughly speaking.
So you're shrinking this thing to a finite region and then gluing many of them?
Yes, you have to compactify, right? Because the point is there isn't now one Zhukovsky plane, because why should you restrict momentum to be to 0 to 2 pi? You shouldn't. The momentum can take.
Right. So now you have quite complicated physical region.
Yeah. Yeah.
How does the crossing act?
Yes. So you go inside. So it's, if you remember with crossing going inside the circle.
Yeah.
You go inside. Yeah.
Goes to 1 over x.
But it goes to 1 over x right. So it's a little bit more complicated. I was hoping not to show you this, but essentially there are equivalent there are contours inside, and you go to, if you started off with a physical momentum, you will go to some guy inside the scallion or inside the kidney. And you go through, and in practical terms, for example, the simple parts where you're going through, the odd crossing or the massless crossing or the mixed mass crossing, it's just conceptually the usual Sahotsky-Plemelli theorem, where you're just going through and you're picking up whatever you need to pick up, right?
Okay, just to be sure that I understood. So you have x left, you have x right, and under the map, x left goes to 1 over x right. The outer region goes to the inner region.
Yes.
Okay.
Yes.
Okay. Very interesting. Yeah. Right.
Bogdan, sorry, I'm always confused about your gluing. You see this complex plane is a non-compact. You can glue only if you have boundary. So I'm missing something in what you're saying.
Well, I guess all I'm saying is that the Zhukovsky variables, which are so wonderful in the Ramon case, are still very nice here, right? Because I can express the S matrix in terms of them. But ultimately, the physical quantity is the momentum. And so what I'm suggesting is that the correct way to use Zhukovsky variables in mixed flux is by gluing them in this kind of way, like you would do with tan. You know, you could plot, I could do the same contour plotting for tan of theta, and let theta not go from 0 to 2 pi, but let it go from, you know, minus infinity to plus infinity, and then start connecting those strips. So basically, if someone smarter than me could come up with a better variable, that what I'm saying is there must be some better variable, which will, you know, no need for gluing Zhukovskys, which is just be precisely what is, there'll be just this one compactification of all these Zhukovsky planes.
What command Mathematica are you using? I cannot understand it.
Okay, no, it's not like that. It's you plot. So I don't. This is not me. This is Olaf. So you should really direct the questions to him in terms of how you produce this figure. But basically, you produce this figure so that of course you don't in practice go to plus or minus infinity. You cut off at something that looks close enough to plus or minus infinity, and then you do the next plot for p between 0 and minus 2 pi, and the next plot between minus 2 pi and minus 4 pi, and you stick those guys together like this.
So if I zoom up into the dash, it's really not continuous there. It's
no, it is
close, but
I mean, sorry. Oh, if you zoom in, because but that's just a practical problem, right? I should map my I should conformally map minus infinity to plus infinity. I should conformally map it to an interval.
Yes.
So it is an infinite cover of a plane.
Yes, 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 yes.
Sounds like log, right?
For example, yes.
So it's not Joukowsky plane, it's log of Joukowsky plane, right? I mean, some OX.
No, I'm showing you the Joukowsky variable itself. I'm showing you what x plus minus looks like as a function of momentum.
Okay.
So instead, look, if you just plotted it on one Joukowsky plane, you could also do the following. Wait, maybe we do it here. If instead you tell Mathematica to do parametric plot for all real momenta, you will get a mess like this. And then it'll, well, if you're going this way, it'll come back. I'll do this wrong, but it'll come out here and go here. And then the next one will come out. Well, no, that's pretty bad. Sorry. The next one will, this guy will come out then on this side, go up and go around. So if you just plotted it in Mathematica, you would get all these stratifications. But that's like plotting tan. They're not really all on one, or log, as Sergey said. They're not really all on one diagram. What's happening as you're going from 0 to 2 pi, and then from 2 pi to 4 pi, you really should be gluing them like this. Because the point 2 pi, right? Imagine you had an excitation with momentum 2 pi minus a little bit. So it would be here and plus a little bit, right? From the point of view of the excitation from the 1 + 1 dimensional quantum field theory, they're not infinitely far apart at all. They're right next to each other. You've just increased the momentum a tiny. So this is somehow the better picture.
Sorry, I got a bit confused about something else, and Alessandro Torrielli authorized me to intervene. So I shift the blame because I promised to shut up. So you said that crossing sends you inside this thick black curve, but inside what region? I mean, there are infinitely many disconnected regions, right?
It depends where you start off with. No. It depends where you start off with. So if you start off,
analytically continue to anywhere, no?
Yes, but I have to give you the right prescription, right? Sure. So there's always the correct prescription for crossing that I have to specify.
And is it always the big one, so to say, or they limit the unbounded?
You can go inside the kidney as well if you want. If you start off near the kidney, you would go inside the kidney instead. But it's
it gives the same thing.
No, there is
the equivalent.
There is a correct. Yeah, there's a correct. That's right. Yeah, so there's a correct way to do it, so that in the first crossed, what the crossed region is specified by that specific analytic continuation.
And do you know whether these other regions have? So one is the correct one. All the other ones they correspond to something physical, or they're just.
I mean, you can cross. No, but no. I mean.
Because
well,
also,
I think, but look, it's a bit similar. Yeah, exactly,
cuts, right?
Exactly. That's what I was going to say.
Cuts.
Yeah.
And there is some interpretation for what they mean, right?
Yeah,
I
don't.
Whether here is the case or.
It's not clear. I mean, for sure there will be some meaning to it, right? Yeah, I just don't. I don't have anything that I can tell you in a useful way. There's a lot that one can try to do.
Okay, well, let me at least stop the recording and give people an opportunity to leave if they want to. So